Imagine a number, not a number you can count on your fingers, or even a number you can write down easily. Imagine a number so vast, so utterly incomprehensible, that your brain, a product of a world measured in steps and miles, simply refuses to hold it. This number is the distance light travels in a single year. It is the yardstick of the cosmos, the unit that defines our place in the universe, and the concept that fundamentally breaks our human intuition. We call it the light year. It is a distance of nearly 6 trillion miles, or 9.46 trillion kilometers, but that is just the definition. The reality is a profound, mind-bending truth. When we look out into the night sky, we are not seeing the universe as it is now, but as it was. Every star, every galaxy is a ghost of its former self, a time capsule of light that has traveled for years, millennia, or even eons to reach our eyes. We are not just looking across space, we are looking back through time. This is the story of that distance, the speed that governs it, and the cosmic journey that breaks our brains. If you are ready to have your perception of reality fundamentally altered, to journey to the edge of the observable universe and back, then take a moment to like this video and subscribe to CosmoDepth. Your support is the energy that powers our exploration of the cosmos. Now let us begin our journey into the impossible scale of the light year. Our story must begin not with distance, but with speed. The speed of light in a vacuum, denoted by the letter C, is the most fundamental constant in the universe. It is the ultimate speed limit, a cosmic law that cannot be broken. Light travels at an astonishing 299,792,458 meters per second, or roughly 186,282 miles per second. To put that into perspective, a beam of light could circle the Earth 7.5 times in a single second. It can travel from the Earth to the Moon in just over a second. This speed is the foundation of the light year. The light year is simply the distance covered by this constant speed over the period of one Earth year. It is a unit of distance, not time, but it is a distance that is inextricably linked to time. The reason for this cosmic speed limit lies in Albert Einstein's theory of special relativity, published in 1905. Einstein's revolutionary insight was that space and time are not separate entities, but are interwoven into a single four-dimensional fabric called space-time. The speed of light is the constant that connects them. Special relativity dictates that, as an object with mass approaches the speed of light, two things happen. Its mass increases and time slows down for it relative to a stationary observer. The equation that governs this is the Lorentz factor, which shows that as the velocity v approaches the speed of light, say c, the energy required to accelerate the object further approaches infinity. To reach the speed of light, an object with mass would require an infinite amount of energy, which is physically impossible. Only massless particles, like photons, can travel at c. This inviolable speed limit is what makes the light year so mind-bending. It is the barrier that separates us from the rest of the cosmos. It means that interstellar travel, as depicted in science fiction, is not a matter of simply building a faster engine. It is a matter of fundamentally rewriting the laws of physics. The light year is the distance that reminds us of our cosmic isolation, the vast gulf that even the fastest possible speed cannot easily bridge. To truly appreciate the light year, we must understand how astronomers measure it. We cannot simply lay a ruler across the cosmos. Instead, astronomers use a brilliant, overlapping set of techniques known as the cosmic distance ladder. It is called a ladder because each rung relies on the accuracy of the rung below it to measure distances that are progressively farther away. The first, most fundamental rung is radar ranging. For objects within our solar system, like the Moon and the planets, we can bounce radio waves off their surfaces and measure the time it takes for the signal to return. Since radio waves travel at the speed of light, this gives us a highly accurate measure of the distance. This technique is the foundation upon which all other measurements are built. The second rung, and the first to introduce the light year, is stellar parallax. This is the only direct method for measuring the distance to stars. Parallax is the apparent shift in a star's position as the Earth orbits the Sun. Hold your finger out in front of your face and alternate closing your left and right eyes. Your finger appears to jump against the background. Astronomers measure the tiny angle of this shift over a 6-month period. The closer the star, the larger the shift. This method is incredibly precise, but it is limited to stars within about 1,600 light-years, as the parallax angle becomes too small to measure accurately beyond that. Missions like the Gaia Space Observatory have measured the parallax of over 1 billion stars, creating the most accurate 3D map of our local galaxy. The third rung introduces the concept of standard candles. These are objects whose intrinsic brightness, or absolute magnitude, is known. By comparing their known absolute brightness to their observed apparent brightness, astronomers can calculate their distance. It is like knowing the wattage of a light bulb and measuring how dim it appears from a distance. The most crucial standard candle for the middle rungs of the ladder is the Cepheid variable star. These are massive, luminous stars that pulsate rhythmically. In the early 20th century, astronomer Henrietta Swan Leavitt discovered a profound relationship. The longer the period of a Cepheid's pulsation, the brighter its intrinsic luminosity. This period luminosity relationship allows astronomers to determine the absolute brightness of any Cepheid simply by observing how quickly it pulsates. Since Cepheids are incredibly bright, they can be seen in nearby galaxies, allowing us to measure the distance to those galaxies and calibrate the next, higher rung of the ladder. The final, highest rung of the ladder uses the type Ia supernova. These are the spectacular explosions of white dwarf stars that have reached a critical mass. Because they all explode at nearly the same mass, they all have a remarkably uniform peak luminosity, making them excellent standard candles for measuring the distance to the most distant galaxies, out to billions of light years. The observation of these supernovae was what led to the shocking discovery of the accelerating expansion of the universe. The cosmic distance ladder is a masterpiece of scientific ingenuity, a series of overlapping measurements that allows us to confidently place objects across the entire observable universe, from our solar system to the edge of time itself. It is the tool that translates the abstract concept of the light year into a tangible, measurable reality. The most profound consequence of the light year is the time machine effect. Because light travels at a finite speed, every time we look out into the cosmos, we are looking back in time. The light we see from a distant object is not a live feed. It is a historical record, a message from the past. Consider our own sun. It is about 8.3 light minutes away. If the sun were to suddenly vanish, we would not know about it for 8 minutes and 20 seconds. We would continue to see the sun shining brightly in the sky, a ghost of a star that no longer exists. Now, extend that to the stars in the night sky. Alpha Centauri, our nearest stellar neighbor, is about 4.37 light-years away. We see it as it was 4.37 years ago. Betelgeuse, a massive red giant, is about 642 light-years away. If it exploded tonight, we would not witness the spectacular supernova for over 6 centuries. When we look at the Andromeda Galaxy, our nearest large galactic neighbor, which is 2.5 million light-years away, we are seeing it as it was 2.5 million years ago, a time when early hominids were just beginning to walk the Earth. And when we look at the most distant galaxies, those observed by the James Webb Space Telescope, JWST, we are seeing light that has traveled for over 13 billion years. We are seeing the universe as it was just a few 100 million years after the Big Bang, witnessing the birth of the first stars and galaxies. The light year is not just a measure of distance, it is a measure of cosmic history. It is the physical manifestation of the inseparable link between space and time. This means that astronomy is inherently a form of archaeology. We are constantly digging through the layers of time, using light as our shovel to reconstruct the history of the universe. The farther we look, the deeper we delve into the past. The light year is the distance that breaks our brains because it forces us to confront the fact that the universe is not a static place, but a dynamic, evolving entity. And our view of it is always, fundamentally, a view of the past. To truly grasp the scale of the light year, we must first attempt to break down the sheer magnitude of the number, 9.46 trillion kilometers, into something a human brain can process. Let us start with the fastest human-made object ever launched, the Parker Solar Probe, which has reached speeds of over 690,000 kilometers per hour. If we could somehow maintain that speed and point it toward Alpha Centauri, our nearest star, it would still take over 6,600 years to cover the 4.37 light-years. The entire span of recorded human history would pass by before the probe reached its destination. Consider the Voyager 1 spacecraft, currently the most distant human-made object from Earth, traveling at about 61,000 kilometers per hour. It has been traveling for nearly 50 years, yet it has not even covered the distance of a single light day. A light day is the distance light travels in 24 hours, about 16 billion miles. Voyager 1 would take over 17,000 years to cover a single light year. The light year is a distance that makes all our terrestrial measures, miles, kilometers, even the distance to the moon, seem utterly trivial. The distance to the moon is about 1.3 light seconds. The distance to Mars, at its closest, is about 3 light minutes. The entire solar system, out to the Oort cloud, the vast spherical shell of icy bodies that defines the gravitational boundary of our Sun, is estimated to be about 1 to 2 light-years in diameter. Even our entire home system is barely a single step on the cosmic scale. The light year is the unit that forces us to abandon our human-centric view of the world. It is the distance that reminds us that we are not just small, but infinitesimally small, living on a tiny pale blue dot in a cosmos of unimaginable scale. The very act of trying to visualize this distance is the point where our brains begin to break, where the familiar rules of our world dissolve into the abstract reality of the universe. Let us delve deeper into the mechanics of the cosmic distance ladder, as it is the key to unlocking the true scale of the light year. The transition from the local, direct measurement of parallax to the indirect, statistical methods for the deep cosmos is the most crucial step. Parallax, as measured by the Gaia mission, is a geometric method, relying on the simple trigonometry of the Earth's orbit. It is the gold standard, but it fails beyond a certain distance. To bridge this gap, we rely on the standard candles. The Cepheid variables, as discovered by Henrietta Swan Leavitt, are the first true cosmic bridge. Leavitt's work on the Cepheids in the Small and Large Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, showed that the brighter the star, the slower it pulsates. This period luminosity relationship allows astronomers to determine the absolute brightness of any Cepheid simply by observing how quickly it pulsates. Since Cepheids are incredibly bright, they can be seen in nearby galaxies, allowing us to measure the distance to those galaxies and calibrate the next higher rung of the ladder. But for the truly deep cosmos, we need a brighter candle. The type Ia supernova. These are the spectacular explosions of white dwarf stars that have reached a critical mass. Because they all explode at nearly the same mass, they all have a remarkably uniform peak luminosity, making them excellent standard candles for measuring the distance to the most distant galaxies, out to billions of light years. The observation of these supernovae was what led to the shocking discovery of the accelerating expansion of the universe. The final rung of the ladder is not a candle, but a law, Hubble's law. This law, discovered by Edwin Hubble in the late 1920s, states that the farther away a galaxy is, the faster it is receding from us. This is a direct consequence of the expansion of the universe. By measuring the redshift of a distant galaxy, the stretching of its light waves due to the expansion of space, astronomers can determine its recession velocity. Using Hubble's law, this velocity can be translated into a distance. This method is calibrated by the type Ia supernovae, which provide the known distances needed to determine the value of the Hubble constant, the rate of the universe's expansion. The cosmic distance ladder is a masterpiece of scientific ingenuity, a series of overlapping measurements that allows us to confidently place objects across the entire observable universe, from our solar system to the edge of time itself. It is the tool that translates the abstract concept of the light year into a tangible, measurable reality. The light year is a measure of distance for a stationary observer, but what about a traveler moving at relativistic speeds? This is where the concept of the light year truly breaks our brains, as it forces us to confront the relativity of distance. For a traveler moving at a significant fraction of the speed of light, the universe fundamentally changes. According to special relativity, as an object's velocity increases, the space in front of it appears to contract in the direction of motion. This is known as Lorentz contraction. Imagine a spaceship traveling at 99.9 .99999999999% the speed of light. For an observer on Earth, the journey to a star 100 light-years away would take just over 100 years. But for the astronaut on the ship, the distance of 100 light-years would appear to contract to just a few meters. The journey would take only a few minutes of the astronaut's subjective time. This is the ultimate paradox of the light year. The distance is not an absolute fixed quantity. It is dependent on the observer's state of motion. The light year is a vast, insurmountable barrier for us, the stationary observers. But for the hypothetical relativistic traveler, the universe shrinks, and the light year becomes a trivial distance. This phenomenon is a direct consequence of the constancy of the speed of light. Since the speed of light must be the same for all observers, the only way to reconcile the different measurements of time and distance is for time to slow down and space to contract. The light year is the distance that reminds us that our perception of space and time is merely a local, low-speed approximation of a much deeper, more complex reality. The light year is the distance that forces us to think in terms of space-time, where distance and duration are two sides of the same relativistic coin. The light year is the unit that defines the size of the observable universe. This is the sphere of space, centered on Earth, from which light has had time to reach us since the Big Bang. The universe is 13.8 billion years old. Therefore, the most distant light we can see has traveled for 13.8 billion years. This might lead one to assume the radius of the observable universe is 13.8 billion light-years. But this is where the expansion of the universe, governed by Hubble's law and dark energy, complicates the light year. During the 13.8 billion years that the light has been traveling toward us, the space it is traveling through has been expanding. The source of that light, the most distant galaxies, are now much farther away than 13.8 billion light-years. The current estimated distance to the edge of the observable universe is about 46.5 billion light-years. This is the ultimate light-year limit. It is the distance that defines the boundary of our knowledge, the point beyond which the light has not yet had time to reach us. Everything we know about the cosmos, the galaxies, the cosmic web, the CMB, is contained within this 46.5 billion light-year sphere. The light year is the distance that reminds us of our cosmic isolation. The universe itself is likely much, much larger, perhaps infinite, but the light year defines the boundary of our perception. The galaxies beyond the 46.5 billion light-year horizon are receding from us at a speed greater than the speed of light. Not because they are moving through space that fast, but because the space between us and them is expanding that fast. The light from those galaxies will never reach us. The light year is the distance that defines the ultimate, uncrossable boundary of our observable reality. The light year is not just a scientific concept, it carries a profound philosophical weight. It forces us to confront the nature of time, distance, and our own existence. The time machine effect means that the universe is a place of ghosts. When we look at the stars, we are seeing things that may no longer exist. The light year is the distance that makes us realize that the concept of now is meaningless on a cosmic scale There is no universal now. The now of a distant galaxy is a concept that is fundamentally unknowable to us. This realization has a profound effect on our perception of reality. It means that the universe is not a single, unified entity, but a collection of historical moments, each separated by the vast gulf of the light year. The light year is the distance that reminds us that we are living in a universe of temporal separation. Furthermore, the light year is the distance that defines the scale of our cosmic insignificance. Our entire planet, our entire civilization, is a tiny, fleeting moment in a cosmos measured in billions of light years and billions of years. The light year is the distance that forces us to abandon our anthropocentric view and embrace the vast, indifferent scale of the universe. Yet, there is a profound beauty in this realization. The light year is the distance that allows us to be cosmic archaeologists. It is the distance that brings us the light of the Big Bang, the light of the first stars, the light of the birth of galaxies. The light year is the distance that connects us to the entire history of the universe. The philosophical weight of the light year is the weight of existence itself, a reminder that we are a conscious part of a vast, ongoing, and ancient cosmic drama. The story of the light year is also a story of human ingenuity, a history of scientists slowly, painstakingly chipping away at the cosmic darkness. For most of human history, it was assumed that the speed of light was infinite. The first person to successfully measure the speed of light was the Danish astronomer Ole Rømer in 1676. He observed the eclipses of Io, one of Jupiter's moons. He noticed that the time between eclipses varied depending on whether the Earth was moving toward or away from Jupiter. When the Earth was moving away, the light from Io had to travel a greater distance, causing the eclipses to appear later. Rømer used the diameter of the Earth's orbit and the time delay to calculate a speed of light that was remarkably close to the modern value, proving that light travels at a finite speed. This was the first crucial step toward defining the light year. The next major step came with the development of parallax measurement in the 19th century. After centuries of failed attempts, Friedrich Bessel successfully measured the parallax of the star 61, Cygni, in 1838, finally providing the first reliable distance to a star outside our solar system. This measurement, expressed in the unit of the parsec, a distance related to parallax, equal to about 3.26 light years, was the first time the true vast scale of interstellar space was quantified. The final revolutionary step was the work of Henrietta Swan Leavitt and Edwin Hubble. Leavitt's discovery of the period luminosity relationship for Cepheid variables provided the first reliable standard candle for measuring intergalactic distances. Hubble then used Leavitt's work to measure the distance to the Andromeda Nebula, proving it was a separate galaxy millions of light years away. This single measurement expanded the known universe by an unimaginable factor, fundamentally establishing the light year as the essential unit of cosmic scale. The light year is not just a number, it is a legacy of human curiosity, a testament to the power of observation, and a reminder that our understanding of the cosmos is built on the shoulders of giants who dared to question the infinite. The light year is defined by the speed of light, But the speed of light itself is a deep mystery rooted in the quantum realm. The speed of light is not just a velocity, it is a manifestation of the fundamental properties of space-time and the quantum fields that permeate it. In quantum field theory, light is composed of photons, the massless particles that are the quanta of the electromagnetic field. The speed of light is the speed at which a disturbance in the electromagnetic field propagates through the vacuum. The fact that the speed of light is constant for all observers is a direct consequence of the structure of space-time, as described by the Minkowski metric. This metric defines the geometry of space-time and ensures that the space-time interval between any two events is the same for all inertial observers. The speed of light is the maximum speed at which information can travel in this geometry. Furthermore, the speed of light is related to the fundamental constants of the universe, the permittivity of free space, epsilon naught, and the permeability of free space, mu naught. The speed of light is defined as c equals 1 divided by the square root of the quantity, epsilon, naught times mu naught. This means that the speed of light is not an arbitrary number. It is determined by the fundamental electrical and magnetic properties of the vacuum itself. The light year is the distance that forces us to confront the deepest mysteries of physics. It is the distance that is defined by the very fabric of space-time and the quantum nature of reality. The light year is the distance that reminds us that the vastness of the cosmos is intrinsically linked to the smallest, most fundamental constants of nature. The light year is the unit that allows us to quantify the most dramatic feature of the cosmos, the expansion of the universe. As we established, Hubble's law links the distance of a galaxy, measured in light years, to its recession velocity, measured by its redshift. The farther the galaxy, the faster it is receding from us. This is not because the galaxies are moving through space, but because the space between them is expanding. This expansion means that the light year is a constantly changing measure. The distance to a galaxy 10 billion light years away is not a fixed number. It is a distance that has grown over the 10 billion years the light has been traveling. Cosmologists use two different measures of distance to account for this. The co-moving distance, the distance as it would be measured today if the expansion were stopped, and the look-back time, the time the light has taken to reach us. The light year is the distance that allows us to track the history of this expansion. By measuring the distances to type Wire supernovae at different look-back times, astronomers have been able to map the entire expansion history of the universe, leading to the discovery of dark energy, the mysterious force that is accelerating the expansion. The light year is the distance that defines the ultimate fate of the universe. If the expansion continues to accelerate, the light from all but the most local galaxies will eventually be stretched so much that it will become undetectable. The light year is the distance that will eventually define the cosmic horizon that shrinks around us, leaving our descendants in a cold, dark, and empty universe. The light year is the distance that tells the story of the universe's beginning, its present, and its inevitable end. The light year is the distance that defines the challenge of the search for extraterrestrial intelligence, SETI. Our nearest star, Alpha Centauri, is 4.37 light-years away. If a civilization on a planet orbiting Alpha Centauri were to send us a radio signal today, it would take 4.37 years for that signal to reach us. If we were to respond immediately, it would take another 4.37 years for our response to reach them. A simple conversation would take nearly 9 years. Now, consider the vastness of the Milky Way, which is about 100,000 light-years in diameter. A signal from a civilization on the opposite side of the galaxy would take 100,000 years to reach us. Any conversation would span hundreds of thousands of years, a duration that dwarfs the entire span of human civilization. The light year is the distance that makes interstellar communication a matter of cosmic patience. It means that any communication we receive will be a message from a distant past, and any message we send will be a message to a distant future. The light year is the distance that forces us to confront the profound loneliness of the cosmos, the vast gulf of space and time that separates us from any potential neighbors. The light year is the distance that defines the challenge of interstellar travel. Even with the most ambitious proposals, like the Breakthrough Starshot Initiative, which aims to send tiny probes to Alpha Centauri at 20% the speed of light, the journey would still take over 20 years. The light year is the distance that reminds us that for now, we are confined to our tiny corner of the cosmos, a small, pale, blue dot in a universe of unimaginable scale. The light year is the unit that allows us to map the cosmic web, the largest structure in the universe. The cosmic web is the vast filamentary structure of galaxies, clusters, and superclusters, separated by immense, empty voids. The typical size of a galaxy cluster is measured in millions of light years. The filaments that connect these clusters can span hundreds of millions of light years. The voids, the empty spaces between the filaments, can be over 1 billion light years across. The light year is the distance that allows us to see the structure of the universe. The Sloan Digital Sky Survey, SDSS, which has mapped the positions of millions of galaxies, uses the light year to create a 3-dimensional map of this web. This map shows that galaxies are not randomly distributed. They are clustered along the filaments, the highways of the universe, and are conspicuously absent from the voids. The light year is the distance that allows us to see the history of this structure. The light from the most distant parts of the cosmic web has traveled for billions of light years, showing us the web as it was when the universe was young. We can see how the structure has evolved over cosmic time, how the small, early clumps of galaxies have merged and grown into the massive clusters and superclusters we see today. The light year is the distance that defines the scale of the universe's architecture. It is the distance that reminds us that the universe is not a static place, but a dynamic, evolving structure, a vast, intricate web woven from the fabric of space-time. The light year is the distance that fundamentally challenges our human perception. Our brains evolved to navigate a world measured in meters and seconds, a world where the speed of light is effectively infinite. When we try to visualize a light year, our brains resort to familiar, but ultimately inadequate, analogies. We can imagine a journey across a country, or even around the world, but the jump from a few thousand kilometers to 9.46 trillion kilometers is a leap into the abstract. The light year is the distance that forces us to think in terms of logarithmic scale, where each step is a multiplication, not an addition. The light year is the distance that makes us realize the limitations of our intuition. Our intuition is a product of our low-speed, local environment. It tells us that time is absolute, that distance is fixed, and that nothing can travel faster than a speeding bullet. The light year and the physics that defines it tells us that all of these intuitions are wrong. Time is relative, distance is contracted, and the speed of light is the ultimate, uncrossable barrier. The light year is the distance that forces us to rely on mathematics to understand reality. We cannot visualize the vastness of the cosmos, but we can quantify it with equations. The light year is the distance that reminds us that the true nature of reality is not intuitive, but mathematical. The light year is the distance that breaks our brains, but in doing so, it forces us to use the most powerful tool we possess, our capacity for abstract thought. To further break down the light year, we can translate the vast distances into a more relatable unit of time, the cosmic calendar. Imagine the entire 13.8 billion year history of the universe compressed into a single Earth year. On this scale, the light year takes on a new temporal significance. January 1st, midnight, the Big Bang. May, the Milky Way galaxy begins to form. September 3rd, our Sun and solar system form. September 21st, life appears on Earth. December 25th, the dinosaurs appear. December 31st, 11:59:46 p.m. The entire span of recorded human history. On this scale, the light year is the distance that defines the speed of the cosmic narrative. The light from the most distant galaxies, which has traveled for 13 billion light years, is the light that was emitted in the first few months of the cosmic calendar. The light from the Andromeda galaxy, 2.5 million light years away, is the light that was emitted just a few hours ago on December 31st. The light year is the distance that allows us to see the entire cosmic narrative unfold. It is the distance that reminds us that we are living in a universe of immense age and that our own existence is a tiny, fleeting moment in a vast, ongoing cosmic drama. The light year is the distance that gives us perspective, a reminder that the entire history of our civilization is a mere blink of an eye on the cosmic calendar. The light year is the distance that destroys the concept of simultaneity. In our everyday lives, we assume that two events happening at the same time in different locations are truly simultaneous. But the light year and the finite speed of light proves this assumption to be false. Imagine two events. Event A, a supernova 10 light years away, and Event B, a star forming 20 light years away. For an observer on Earth, the light from Event A will reach us 10 years after the event occurred, and the light from Event B will reach us 20 years after the event occurred. Now, imagine a spaceship traveling at a high, relativistic speed between the two events. Due to the relativity of time and distance, the order of the two events can actually be reversed for the traveling observer. For the astronaut, Event B might appear to happen before Event A. This is the ultimate consequence of the light year and the speed of light. The concept of simultaneous is not absolute. It is relative to the observer's state of motion. The light year is the distance that reminds us that the universe is not a single, unified entity, but a collection of events whose temporal order is dependent on the observer. The light year is the distance that forces us to abandon the intuitive notion of a universal now and embrace the complex, interwoven reality of space-time. The light year is the distance that defines the challenge of interstellar travel, but it is also the distance that inspires the most ambitious technological dreams. Since the speed of light is an absolute barrier, any realistic form of interstellar travel must involve either extremely long travel times or a way to circumvent the laws of physics as we currently understand them. The most realistic near-term proposal is the Breakthrough Starshot Initiative, which aims to use powerful lasers to propel tiny gram-scale probes to 20% the speed of light. Even at this speed, the journey to Alpha Centauri would take over 20 years. This is a testament to the sheer scale of the light year. The more speculative science fiction concepts, warp drives and wormholes, are attempts to cheat the light year. A warp drive, as theorized by physicist Miguel Alcubierre, would not move the spaceship through space faster than light, but would instead warp the space-time around the ship, contracting space in front and expanding it behind. The ship itself would remain stationary within its local bubble of space-time, thus circumventing the speed limit. However, the energy requirements for such a feat are astronomical, requiring the mass energy of an entire planet or more, and it requires the existence of exotic matter with negative mass energy density. A wormhole is a hypothetical tunnel through space-time that could connect two distant points, effectively reducing the light-year distance to a trivial length. While mathematically possible within the framework of general relativity, the creation and stabilization of a wormhole would also require exotic matter and immense energy. The light year is the distance that defines the ultimate technological challenge for humanity. It is the distance that reminds us that our current technology is utterly inadequate for traversing the cosmos. But it is also the distance that inspires us to push the boundaries of physics, to find a way to make the light year a manageable distance, and to finally break free of our cosmic isolation. The light year is the distance that allows us to see the cosmic microwave background, CMB, the oldest light in the universe. The CMB is the light that was emitted when the universe was just 380,000 years old, when it cooled enough for electrons and protons to combine into neutral atoms, making the universe transparent. This light has been traveling for 13.8 billion years, and it has been stretched by the expansion of space, shifting its wavelength from visible light to microwaves. The light year is the distance that defines the CMB's location. The CMB is not a distant wall. It is the light that was emitted from every point in space 13.8 billion years ago. When we look out in any direction, we are looking back 13.8 billion light years in time, to the moment the universe became transparent. The CMB is the ultimate light-year measurement, the distance that defines the boundary of the visible universe. The light year is the distance that allows us to see the initial conditions of the universe. The tiny temperature fluctuations in the CMB, which represent the seeds of all future structure, are a direct consequence of the light year. The distance that separates these fluctuations and the time it took for the light to reach us is what allows us to map the early universe and understand how the cosmos evolved from a smooth, uniform state to the clumpy, structured universe we see today. The light year is the distance that connects us to the very beginning of time. The light year is the unit that allows us to quantify the most dramatic feature of the cosmos, the expansion of the universe. As we established, Hubble's law links the distance of a galaxy, measured in light years, to its recession velocity, measured by its redshift. The farther the galaxy, the faster it is receding from us. This is not because the galaxies are moving through space, but because the space between them is expanding. This expansion means that the light year is a constantly changing measure. The distance to a galaxy 10 billion light years away is not a fixed number. It is a distance that has grown over the 10 billion years the light has been traveling. Cosmologists use two different measures of distance to account for this. The comoving distance, the distance as it would be measured today if the expansion were stopped, and the look-back time, the time the light has taken to reach us. The light year is the distance that allows us to track the history of this expansion. By measuring the distances to Type Ia supernovae at different look-back times, astronomers have been able to map the entire expansion history of the universe, leading to the discovery of dark energy, the mysterious force that is accelerating the expansion. The light year is the distance that defines the ultimate fate of the universe. If the expansion continues to accelerate, the light from all but the most local galaxies will eventually be stretched so much that it will become undetectable. The light year is the distance that will eventually define the cosmic horizon that shrinks around us, leaving our descendants in a cold, dark, and empty universe. The light year is the distance that tells the story of the universe's beginning, its present, and its inevitable end. While the light year is the most intuitive unit of cosmic distance, astronomers often prefer to use the parsec, PC. The parsec is a unit that is directly related to the geometric method of parallax, making it a more natural unit for professional astronomy. A parsec is defined as the distance at which one astronomical unit, the average distance from the Earth to the Sun, subtends an angle of 1 arcsecond. This is a highly technical definition, but the key takeaway is the conversion. 1 parsec is equal to approximately 3.26 light years. The use of the parsec is a reminder that the light year, while philosophically profound, is a unit that is derived from the speed of light and the duration of an Earth year. The parsec, on the other hand, is a unit that is derived from the geometry of the Earth's orbit, the most fundamental measurement in the cosmic distance ladder. Astronomers use kiloparsecs, kpc, for distances within the Milky Way. The center of the galaxy is about 8 kiloparsecs away. Megaparsecs, MPC, for distances to nearby galaxies. Andromeda is about 0.78 megaparsecs away. And gigaparsecs, GPC, for the largest scales of the observable universe. The light year is the distance that breaks our brains, but the parsec is the distance that allows astronomers to do the math. The two units are two sides of the same coin, both essential for quantifying the vast, mind-bending scale of the cosmos. The light year is the distance that forces us to confront the limits of the human mind. Our cognitive architecture is simply not designed to process numbers of this magnitude. Psychologists and cognitive scientists have studied how humans perceive large numbers, and the consensus is that our brains struggle to distinguish between, say, 1 billion and 1 trillion. We can write the numbers, We can manipulate them mathematically, but we cannot truly feel the difference in scale. The light year, with its 12 zeros, is a number that exists in the realm of the abstract, beyond the reach of our evolved intuition. The light year is the distance that reminds us that our greatest tool for understanding the cosmos is not our intuition, but our capacity for abstraction. It is the ability to create mathematical models, to use analogies, and to rely on the collective knowledge of the scientific community that allows us to grasp the scale of the light year. The light year is the distance that forces us to embrace the humility of our position. We are small, our lives are short, and our minds are limited. But the light year is also the distance that inspires us to transcend those limits, to use our intellect to explore a cosmos that is fundamentally beyond our immediate comprehension. The light year is the distance that breaks our brains, but in doing so, it opens the door to a deeper, more profound understanding of reality. The light year is the distance that defines the cosmic horizon, the ultimate boundary of the observable universe. The cosmic horizon is not a physical edge to the universe. It is a boundary of our knowledge, a limit imposed by the finite speed of light and the finite age of the cosmos. Everything we have discussed, the galaxies, the cosmic web, the CMB, is contained within this 46.5 billion light-year sphere. The light year is the distance that reminds us of our cosmic isolation. The universe itself is likely much, much larger, perhaps infinite, but the light year defines the boundary of our perception. The galaxies beyond the 46.5 billion light-year horizon are receding from us at a speed greater than the speed of light. Not because they are moving through space that fast, but because the space between us and them is expanding that fast. The light from those galaxies will never reach us. The light year is the distance that defines the ultimate, uncrossable boundary of our observable reality. The light year is the distance that defines the ultimate fate of the universe. If the expansion continues to accelerate, the light from all but the most local galaxies will eventually be stretched so much that it will become undetectable. The light year is the distance that will eventually define the cosmic horizon that shrinks around us, leaving our descendants in a cold, dark, and empty universe. The light year is the distance that tells the story of the universe's beginning, its present, and its inevitable end. The light year is the distance that reminds us that the universe is not a static place, but a dynamic, evolving entity, and our view of it is always, fundamentally, a view of the past. The light year is the distance that allows us to map the distribution of dark matter, the invisible scaffolding of the cosmos. The existence of dark matter is inferred from its gravitational effects on the visible matter. By measuring the rotation curves of galaxies and the gravitational lensing of distant galaxies, astronomers can map the distribution of dark matter across vast distances, measured in millions of light years. The light year is the distance that allows us to see the structure of the dark matter web. The filaments and nodes of the cosmic web, which are the largest structures in the universe, are defined by the distribution of dark matter. The light year is the distance that allows us to see the invisible, to map the structure of a substance that does not emit, absorb, or reflect light. The light year is the distance that reminds us that the universe is far stranger than we can easily comprehend. the vast majority of the cosmos is composed of things we cannot see, and the light year is the unit that allows us to quantify the scale of this cosmic mystery. The light year is the distance that fundamentally destroys the concept of a universal now. Because the speed of light is finite, the concept of two events happening at the same time in different locations is not absolute. It is relative to the observer's state of motion. The light year is the distance that reminds us that the universe is not a single unified entity, but a collection of historical moments, each separated by the vast gulf of the light year. The light year is the distance that forces us to confront the fact that the universe is a place of temporal separation. The now of a distant galaxy is a concept that is fundamentally unknowable to us. The light year is the distance that reminds us that we are living in a universe of ghosts, where every point of light is a message from the past. The light year is the distance that inspires us to embrace the relativity of reality. It is the distance that reminds us that our perception of space and time is merely a local, low-speed approximation of a much deeper, more complex reality. The light year is the distance that breaks our brains, but in doing so, it opens the door to a deeper, more profound understanding of the cosmos. While the cosmic distance ladder is a masterpiece of scientific ingenuity, it is not without its limitations, and the light year is the unit that exposes these flaws. The primary limitation is the cumulative error. Each rung of the ladder is calibrated by the rung below it. Any small error in the measurement of the first rung, radar ranging, is magnified as we climb the ladder to the most distant galaxies. The light year is the distance that reminds us that our measurements of the deep cosmos are inherently uncertain. The second limitation is the Hubble tension. The value of the Hubble constant, the rate of the universe's expansion, is measured in two different ways. Local measurements, using the cosmic distance ladder, Cepheids, and type Ia supernovae, to measure the distances to nearby galaxies. Early universe measurements, using the cosmic microwave background, CMB, to infer the expansion rate of the early universe. These two measurements yield significantly different values, a discrepancy known as the Hubble tension. The light year is the distance that defines this tension, a profound disagreement between our local and global measurements of the cosmos. The light year is the distance that reminds us that our understanding of the universe is still incomplete, and that there may be new physics waiting to be discovered. The light year is the distance that carries a profound philosophical weight of scale. It is the distance that forces us to confront the fact that the universe is not a single, unified entity, but a collection of historical moments, each separated by the vast gulf of the light year. The light year is the distance that reminds us that the concept of now is meaningless on a cosmic scale. There is no universal now. The now of a distant galaxy is a concept that is fundamentally unknowable to us. This realization has a profound effect on our perception of reality. It means that the universe is not a single unified entity, but a collection of historical moments, each separated by the vast gulf of the light year. The light year is the distance that reminds us that we are living in a universe of temporal separation. Furthermore, the light year is the distance that defines the scale of our cosmic insignificance. Our entire planet, our entire civilization, is a tiny, fleeting moment in a cosmos measured in billions of light years and billions of years. The light year is the distance that forces us to abandon our anthropocentric view and embrace the vast, indifferent scale of the universe. Yet, there is a profound beauty in this realization. The light year is the distance that allows us to be cosmic archaeologists. It is the distance that brings us the light of the Big Bang, the light of the first stars, the light of the birth of galaxies. The light year is the distance that connects us to the entire history of the universe. The philosophical weight of the light year is the weight of existence itself, a reminder that we are a conscious part of a vast, ongoing, and ancient cosmic drama. The light year is the distance that defines the future of cosmology. The next generation of telescopes and space missions are all designed to push the boundaries of the light year, to see farther back in time, and to measure the expansion of the universe with greater precision. The James Webb Space Telescope, JWST, is already pushing the light-year limit, observing galaxies that existed just a few 100 million years after the Big Bang. The light from these galaxies has traveled for over 13 billion light-years, allowing us to witness the birth of the first stars and galaxies. The Nancy Grace Roman Space Telescope will use the light year to map the distribution of dark matter and dark energy across vast distances, using gravitational lensing and type-wire supernovae to measure the expansion history of the universe with unprecedented accuracy. The Square Kilometre Array, SKA, will use the light year to map the distribution of neutral hydrogen in the early universe, allowing us to see the cosmic dark ages, the period before the first stars ignited. The light year is the distance that reminds us that the universe is a place of constant discovery. It is the distance that inspires us to build bigger telescopes, to develop new theories, and to continue the quest to understand the vast, mind-bending scale of the cosmos. The light year is the distance that defines the ultimate goal of human curiosity. The light year is the distance that allows us to visualize the structure of space-time through the concept of the light cone. A light cone is a geometric representation of the path that light takes through space-time. For any event in space-time, the light cone defines the region of space-time that can be influenced by that event, the future light cone, and the region of space-time that could have influenced that event, the past light cone, light cone. The light year is the distance that defines the slope of the light cone. Since light travels at a constant speed, the light cone is a perfect 45-degree angle in a space-time diagram. Everything that has ever happened to us is contained within our past light cone, and everything we can ever influence is contained within our future light cone. The light year is the distance that reminds us that the universe is a place of causality. The speed of light is the maximum speed at which cause and effect can propagate. The light year is the distance that defines the boundaries of our influence and the limits of our knowledge. The light year is the distance that forces us to confront the fact that the universe is a place of profound, unchangeable history. The light year is defined by the speed of light, but the precise measurement of RCE is a story of relentless human ingenuity, a quest that spanned centuries and involved some of the most delicate experiments ever conceived. After Romer's initial astronomical estimate, the next major breakthrough came in the mid-19th century with the first successful terrestrial measurements. Hippolyte Fizeau, in 1849, devised an ingenious experiment using a rapidly rotating toothed wheel. he shone a beam of light through the gaps in the wheel, sent it to a distant mirror, and had it reflect back. By precisely controlling the wheel's rotation speed, he could make the returning light pass through the next gap or be blocked by the next tooth. This allowed him to calculate the time it took for the light to travel the known distance, yielding a value for c within about 5% of the modern value. A year later, Léon Foucault refined this method, replacing the toothed wheel with a rotating mirror. This was a far more precise technique, as the angle of the mirror's rotation could be measured with greater accuracy than the speed of the wheel. Foucault's result was even closer to the accepted value, and his method was so sensitive that he could even measure the speed of light in water, proving that light travels slower in water than in air, a crucial piece of evidence supporting the wave theory of light. The final, definitive measurements were made by Albert Michelson in the late 19th and early 20th centuries. Michelson used a series of highly polished, rotating mirrors and a precisely measured baseline of several miles. His meticulous work, which spanned decades, yielded the most accurate value for Sia at the time. His experiments, particularly the famous Michelson-Morley experiment, which we will discuss shortly, not only refined the value of CE, but also laid the experimental foundation for Einstein's theory of special relativity. The light year is a unit born from this relentless, centuries-long pursuit of a single, constant number. The light year's foundation, the constant speed of light, was not easily accepted. Before Einstein, physicists believed that light, being a wave, must travel through a medium, which they called the luminiferous ether or ether. They believed that the speed of light should be relative to this stationary, invisible medium, much like the speed of sound is relative to the air. The Michelson-Morley experiment of 1887 was designed to detect the Earth's motion through this hypothetical ether. The experiment was a masterpiece of precision, using an interferometer to split a beam of light and send the two resulting beams down perpendicular paths before recombining them. The idea was that if the Earth was moving through the ether, the light traveling parallel to the Earth's motion would be slightly slower than the light traveling perpendicular to it, creating a measurable interference pattern. The result was one of the most famous null results in the history of science. No difference was detected. The speed of light was the same regardless of the Earth's motion. This was a profound, shocking result that shattered the ether theory and paved the way for Einstein. Einstein's genius was to take this experimental fact, the constancy of the speed of light, and elevate it to a fundamental postulate of the universe. The light year is the distance that reminds us that the speed of light is not relative to anything. It is an absolute constant, a fixed property of the universe itself, and the reason why our concepts of space and time must be relative. To truly bridge the vast gulf of the light year, the cosmic distance ladder requires more than just Cepheids and Type Ia supernovae. It needs a variety of secondary standard candles to measure distances to galaxies that are too far for Cepheids but too close for the rare Type Ia supernovae. One such method is the Tully-Fisher relation, which applies to spiral galaxies. This empirical relationship shows that the intrinsic luminosity of a spiral galaxy is directly related to its rotation speed. The faster a spiral galaxy rotates, the more massive it is, and the more massive it is, the more luminous it is. By measuring the rotation speed of a distant spiral galaxy using the Doppler effect, the shift in the light's wavelength, astronomers can infer its absolute brightness and, therefore, its distance in light years. For elliptical galaxies, which do not rotate in a uniform way, astronomers use the Faber-Jackson relation. This relation links the luminosity of an elliptical galaxy to the random motion of its stars, the velocity dispersion. The more massive the elliptical, the faster its stars move, and the more luminous it is. Another crucial secondary candle is the surface brightness fluctuation, SBF method. This technique exploits the fact that the light from a distant galaxy is the sum of the light from its individual stars. The farther away the galaxy, the smoother its surface brightness appears. By measuring the lumpiness or fluctuation in the surface brightness, astronomers can determine the distance to the galaxy. These secondary standard candles are essential for calibrating the higher rungs of the ladder, ensuring that the light-year measurements are consistent across the entire range of cosmic distances. They are the intricate scaffolding that allows us to map the universe in light years, from our local group to the edge of the observable cosmos. The light year is the distance that defines the most pressing crisis in modern cosmology, the Hubble tension. The Hubble constant, h0, is the rate at which the universe is expanding, and it is the key factor in converting a galaxy's redshift into a distance in light years. However, as we mentioned, two different methods of measuring h0 yield two significantly different values. The local universe measurement, the ladder, using the cosmic distance ladder, Cepheids and Type Ia supernovae, the value is around 73 kilometers per second per megaparsec. This is the fast value. The early universe measurement, the CMB, using the cosmic microwave background, CMB, data from the Planck satellite, which relies on the physics of the early universe. The inferred value is around 67 kilometers per second per megaparsec. This is the slow value. The difference is small, only about 9%, but the precision of both measurements is so high that the discrepancy is statistically significant. The light year is the distance that defines this tension, a profound disagreement between our local and global measurements of the cosmos. The light year is the distance that forces us to question our fundamental understanding of the universe. Is there a systematic error in the cosmic distance ladder? Or, more excitingly, is there new physics at play? The tension could be a sign that the universe's expansion rate changed more dramatically than expected in the time between the CMB and the present day, perhaps due to a new form of dark energy or a new particle that influenced the early universe. The light year is the distance that reminds us that our understanding of the cosmos is still incomplete, and that the most profound discoveries often lie in the smallest discrepancies. The light year is the distance that allows us to map the cosmic web, the largest structure in the universe, and to appreciate the vastness of its voids. The voids are the immense, spherical regions of space that are nearly empty of galaxies. They can span hundreds of millions of light years across. The light year is the distance that reminds us that the universe is mostly empty space. If the Milky Way were a single grain of sand, the nearest grain of sand, Andromeda, would be several meters away, and the voids would be vast, empty rooms. The light year is the distance that allows us to study the physics of these voids. the gas within the voids is incredibly tenuous and cold, a relic of the early universe. The light year is the distance that allows us to use the light from distant quasars to probe this gas, using the Lyman alpha forest, a series of absorption lines in the quasar's spectrum, to map the distribution of hydrogen gas across billions of light years. The light year is the distance that reminds us that the universe is a structure built from the bottom up, a vast, intricate web woven from the fabric of space-time. The voids are not just empty, they are the regions that started with a slightly lower density of matter in the CMB, and the relentless pull of gravity from the surrounding denser regions has been slowly draining them of their contents over cosmic time. The light year is the distance that allows us to see this process unfold. The light year is the distance that carries a profound philosophical weight of scale. It is the distance that forces us to confront the fact that the universe is not a single, unified entity, but a collection of historical moments, each separated by the vast gulf of the light year. The light year is the distance that reminds us that the concept of now is meaningless on a cosmic scale. There is no universal now. The now of a distant galaxy is a concept that is fundamentally unknowable to us. This realization has a profound effect on our perception of reality. It means that the universe is not a single, unified entity, but a collection of historical moments, each separated by the vast gulf of the light year. The light year is the distance that reminds us that we are living in a universe of temporal separation. Furthermore, the light year is the distance that defines the scale of our cosmic insignificance. Our entire planet, our entire civilization, is a tiny, fleeting moment in a cosmos measured in billions of light years and billions of years. The light year is the distance that forces us to abandon our anthropocentric view and embrace the vast, indifferent scale of the universe. Yet, there is a profound beauty in this realization. The light year is the distance that allows us to be cosmic archaeologists. It is the distance that brings us the light of the Big Bang, the light of the first stars, the light of the birth of galaxies. The light year is the distance that connects us to the entire history of the universe. The philosophical weight of the light year is the weight of existence itself, a reminder that we are a conscious part of a vast, ongoing, and ancient cosmic drama. The light year is the distance that defines the challenge of interstellar travel, but it is also the distance that inspires the most ambitious technological dreams, chief among them the Alcubierre warp drive. Proposed by Mexican physicist Miguel Alcubierre in 1994, the warp drive is a theoretical solution to the light year problem that does not violate Einstein's special relativity. The key is that the ship itself does not move faster than light through space. Instead, the drive warps the space-time around the ship. Imagine a bubble of space-time surrounding the ship. The Alcubierre drive would contract the space in front of the bubble and expand the space behind it. The ship would effectively be surfing a wave of warped space-time, allowing it to cover vast light-year distances in a short amount of subjective time. Since the ship is stationary within its local bubble, it is not violating the cosmic speed limit. The light year is the distance that reminds us of the immense, almost insurmountable challenges of this concept. The Alcubierre drive requires the existence of exotic matter with negative mass energy density, a substance that has never been observed and may not even be physically possible. Furthermore, the energy requirements for even a modest warp bubble are astronomical, requiring the mass energy of an entire planet or more. And it requires the existence of exotic matter with negative mass energy density. The light year is the distance that defines the ultimate technological challenge for humanity. It is the distance that reminds us that our current technology is utterly inadequate for traversing the cosmos. But it is also the distance that inspires us to push the boundaries of physics, to find a way to make the light year a manageable distance, and to finally break free of our cosmic isolation. The light year is the distance that allows us to visualize the structure of space-time through the concept of the light cone. A light cone is a geometric representation of the path that light takes through space-time. For any event in space-time, the light cone defines the region of space-time that can be influenced by that event, the future light cone, and the region of space-time that could have influenced that event, the past light cone. The light year is the distance that defines the slope of the light cone. Since light travels at a constant speed, the light cone is a perfect 45-degree angle in a space-time diagram. Everything that has ever happened to us is contained within our past light cone, and everything we can ever influence is contained within our future light cone. The light year is the distance that reminds us that the universe is a place of causality. The speed of light is the maximum speed at which cause and effect can propagate. The light year is the distance that defines the boundaries of our influence and the limits of our knowledge. The light year is the distance that forces us to confront the fact that the universe is a place of profound, unchangeable history. We have reached the end of our epic journey, a journey that has taken us from the finite speed of light to the infinite scale of the observable universe. We have seen how the light year is not just a number, but a profound philosophical concept, a measure of time, distance, and the limits of human perception. The light year is the distance that breaks our brains, but in doing so, it opens the door to a deeper, more profound understanding of reality. It is the distance that reminds us that we are small, but our capacity for understanding is vast. It is the distance that connects us to the entire history of the universe, from the Big Bang to the present day. The light year is the distance that inspires us to look up, to wonder, and to continue the quest to understand the cosmos. The night sky is not a static backdrop. It is a living, breathing history book, and every point of light is a word in the greatest story ever told. The light year is the distance that makes the twin paradox a reality, a thought experiment that perfectly illustrates the mind-bending consequences of special relativity. Imagine two identical twins. One, the traveler, embarks on a journey to a star 10 light years away, traveling at 99.9999999% the speed of light. The other, the stayer, remains on Earth. According to the stayer, the journey takes just over 20 years, 10 years out, 10 years back. But for the traveler, due to time dilation, the journey takes only a few weeks. When the traveler returns, they will have aged only a few weeks, while their twin on Earth will have aged 20 years. The light year is the distance that defines the magnitude of this time difference. The greater the distance, the more pronounced the time dilation. The paradox lies in the apparent symmetry. Why doesn't the traveler see the stayer's clock running slow? The resolution lies in the fact that the traveler is the one who undergoes acceleration, turning around, which breaks the symmetry and makes the traveler's frame of reference the one where time is truly dilated. The light year is the distance that reminds us that time is not a universal constant. It is a personal experience, relative to one's state of motion. The light year is the distance that makes the concept of a universal now utterly meaningless. It is the distance that forces us to confront the fact that the universe is a place of temporal separation, where the past, present, and future are not fixed, but are interwoven into the fabric of space-time. The light year is the distance that defines the limits of our observation, but it is also the distance that allows us to see the universe in its entirety, across the full electromagnetic spectrum. When we talk about the light year, we usually think of visible light, but the universe communicates with us in a vast range of wavelengths, each telling a different story about the light year distance. Radio waves, the longest wavelengths, used to map the distribution of cold hydrogen gas across the Milky Way and the cosmic web. The light year is the distance that allows us to see the faint, cold gas that fuels star formation. Infrared light, used to penetrate the thick dust clouds that obscure the center of the Milky Way and the birth of stars. The light year is the distance that allows us to see the universe's hidden nurseries. The JWST is an infrared telescope designed to see the light from the most distant, red-shifted galaxies. X-rays and gamma rays, the shortest, most energetic wavelengths used to observe the most violent events in the cosmos: black holes, supernovae, and active galactic nuclei. The light year is the distance that allows us to see the universe's most extreme phenomena. The light year is the distance that reminds us that the universe is a multi-sensory experience. We are not just limited to the visible light that defines our everyday world. By using the entire electromagnetic spectrum, we can map the light year distance in its entirety, from the coldest gas to the hottest plasma, from the nearest stars to the most distant galaxies. The light year is the distance that defines the cosmic dark ages, the period before the first stars ignited. The CMB, which we see at 13.8 billion light years, is the light from the universe at 380,000 years old. After that, the universe was filled with neutral hydrogen gas, which is opaque to visible light. This period, which lasted for hundreds of millions of years, is the cosmic dark ages. The light year is the distance that defines the challenge of observing this era. The only way to see the dark ages is through the faint, red-shifted signal of neutral hydrogen at a wavelength of 21 centimeters. This signal is incredibly weak, and it is redshifted by the expansion of the universe, making it a formidable observational challenge. The Square Kilometre Array, SKA, is being built to detect this faint signal, to map the distribution of neutral hydrogen across billions of light years, and to witness the birth of the first stars and galaxies. The light year is the distance that reminds us that the universe is a place of constant discovery, and that the greatest stories are often hidden in the deepest darkness. The light year, defined by the speed of light, has found a profound new partner in the form of gravitational waves. These ripples in the fabric of space-time, predicted by Einstein's general relativity, also travel at the speed of light. C. Their discovery by the LIGO and Virgo observatories in 2015 opened a new window onto the cosmos, and with it, a new, independent way to measure the light-year distance. These events, typically the merger of two black holes or two neutron stars, are known as standard sirens. When two neutron stars merge, they emit both gravitational waves and a burst of electromagnetic radiation, light. The gravitational wave signal allows us to directly calculate the absolute distance to the merger without relying on the complex multi-step cosmic distance ladder. This is because the strength of the gravitational wave signal is inversely proportional to the distance it has traveled. The light year is the distance that connects these two signals. The gravitational wave tells us the distance, and the light signal tells us the galaxy the merger occurred in, allowing us to measure the galaxy's redshift. By combining the absolute distance from the gravitational wave with the recession velocity from the light, we can determine the Hubble constant in a single, clean step. This is a revolutionary development. The light year is the distance that is now being measured by two independent cosmic rulers, the electromagnetic spectrum and the gravitational spectrum. The hope is that the standard sirens will provide a definitive third measurement of the Hubble constant, potentially resolving the perplexing Hubble tension that currently plagues cosmology. The light year is the distance that reminds us that the universe is constantly revealing new ways to measure its own vastness. The light year is the distance that defines the boundary of our observable universe, and in doing so, it forces us to confront the philosophical and scientific possibility of the multiverse. The 46.5 billion light-year sphere that defines our observable universe is simply the region from which light has had time to reach us since the Big Bang. But the universe itself is likely much, much larger, perhaps infinite. The light year is the distance that separates our observable bubble from the rest of the cosmos. If the universe is indeed infinite, then there are regions of space separated from us by an unimaginable number of light years that are so far away that the light from them will never reach us. These regions are, for all intents and purposes, separate universes, or at least separate domains that are causally disconnected from us. The light year is the distance that defines the level Wad multiverse, the simplest and most accepted form of the multiverse theory. It is the idea that space is infinite, and therefore every possible configuration of matter must eventually repeat itself. There is a sphere 200 light-years away that is identical to Earth, and a sphere 10 to the power of 118 light-years away that is an exact copy of our entire observable universe. The light year is the distance that reminds us that our reality is a local phenomenon. Our laws of physics, our constants of nature, and our very existence are confined to a bubble of space-time defined by the speed of light and the age of the universe. The light year is the distance that forces us to confront the possibility that our entire cosmic history is just one tiny fleeting moment in an infinite, eternal, and incomprehensible multiverse. To truly grasp the light year in the context of an expanding universe, we must distinguish between the various ways astronomers define distance. The light year is often used as a shorthand for look-back time, but the actual distance to a distant object is a complex dynamic quantity. The proper distance is the distance between 2 points in space at a single moment in cosmic time. This is the distance that would be measured by a hypothetical ruler laid end to end between the 2 points. In an expanding universe, the proper distance to a distant galaxy is constantly increasing. The luminosity distance is the distance inferred from the apparent brightness of a standard candle, like a type Ia supernova. Because the light is stretched by the expansion of space, redshift, and the photons are spread out over a larger area, the luminosity distance is always greater than the proper distance. The angular diameter distance is the distance inferred from the apparent size of an object of known physical size. Because the light from a distant object has traveled for so long, the object appears larger than it would in a non-expanding universe. The light year is the distance that forces us to confront the fact that distance is not a simple static concept. It is a dynamic, evolving quantity that is interwoven with the expansion of space and the flow of time. The light year is the distance that reminds us that the universe is a place of profound, unchangeable history, and that every measurement of distance is a measurement of time. The lambda CDM model is defined by 6 parameters, all of which are determined by measuring the light-year distance to various cosmic phenomena. The Hubble constant, h0, the current rate of expansion measured in light years per second per megaparsec. The density of baryonic matter, omega sub b. The density of ordinary matter, measured by the light-year distance to the cosmic microwave background, cMb. The density of cold dark matter, omega sub c. The density of the invisible scaffolding of the cosmos, also measured by the light-year distance to the cMb. The density of dark energy, omega sub lambda. The density of the mysterious force accelerating the expansion, measured by the light-year distance to type 1 a supernovae. The spectral index, h sub s, the measure of the initial fluctuations in the early universe, measured by the light-year distance to the cMb. The optical depth, tau, the measure of how much the cMb light was scattered by the first stars, measured by the light-year distance to the cMb. The light year is the distance that defines the magnitude of the Fermi paradox, the contradiction between the high probability of extraterrestrial life and the lack of observable evidence. The Milky Way is 100,000 light-years across, containing hundreds of billions of stars. If even a small fraction of these stars host life, and if even a small fraction of that life develops into a technological civilization, the galaxy should be teeming with intelligent life. Yet, when we look out into the cosmos across billions of light-years, we see nothing but silence. The light-year is the distance that defines the challenge of the paradox. If a civilization were to colonize the galaxy at a fraction of the speed of light, the entire Milky Way could be colonized in a few million years, a blink of an eye on the cosmic calendar. The light year is the distance that reminds us that the universe is a place of profound, unchangeable history, and that every measurement of distance is a measurement of time. The light year is the distance that forces us to confront the possibility that we are alone, or that the barriers to interstellar travel and communication are far greater than we can imagine. The light year is the distance that reminds us that the universe is a place of profound, unchangeable history, and that every measurement of distance is a measurement of time. We have explored the light year as a measure of distance and a measure of time, but its most profound meaning lies in its definition of the ultimate cosmic horizon, the boundary of our future knowledge. The light year is the distance that will eventually define the final, uncrossable barrier between us and the rest of the cosmos. As the universe continues its accelerated expansion, driven by dark energy, the space between galaxies is stretching at an ever-increasing rate. The light year is the distance that quantifies this cosmic separation. Currently, we can see galaxies up to 46.5 billion light-years away. But as time goes on, the light from more and more distant galaxies will be stretched to such an extreme degree that it will become undetectable, effectively fading into the cosmic background. The light year is the distance that defines the future cosmic isolation. In the far future, perhaps 1 trillion years from now, the only galaxies visible to our descendants will be those within our own gravitationally bound local group: the Milky Way, Andromeda, and a few dozen dwarf galaxies. All other galaxies will have receded beyond the ultimate cosmic horizon, moving away from us faster than the speed of light. The light year is the distance that reminds us that the universe is not a constant. It is a dynamic, evolving entity, and our view of it is a fleeting moment in its history. Imagine a civilization living 1 trillion years from now. They will look up at a sky that is almost entirely black, save for the few dozen galaxies in their local cluster. They will have no way of knowing about the Big Bang, the cosmic microwave background, or the billions of galaxies that once populated the universe. The light year will have become an insurmountable barrier, a distance that has erased the history of the cosmos. The light year is the distance that defines the heat death of the universe. In this ultimate cold and dark future, the light year will have stretched all the energy and matter into a uniform, low-energy state. The light year is the distance that reminds us that the universe is a place of profound, unchangeable history, and that every measurement of distance is a measurement of time. But even in this ultimate darkness, the light year holds a final, profound meaning. The light from the last stars, the last black holes, and the last particles will still be traveling, defining the light year distance until the very end of time. The light year is the distance that reminds us that even in the face of cosmic annihilation, the fundamental laws of physics, the speed of light, the fabric of space-time, will endure. The light year is the distance that breaks our brains, but in doing so, it forces us to confront the most profound questions of existence: the nature of time, the limits of space, and the ultimate fate of everything. It is the distance that connects us to the entire history of the universe, from the Big Bang to the final, cold silence. And it is the distance that reminds us that our quest for knowledge, our curiosity, and our wonder are the only things that truly transcend the light year. The light year is a distance defined by the speed of light, and this speed, c, is not an arbitrary number. It is a fundamental constant of nature, and its value is inextricably linked to the very possibility of our existence, a concept explored by the anthropic principle. Imagine if the speed of light was slightly different. If c were significantly slower, the universe would be a vastly different place. The light-year distance would shrink, but the time it takes for information to travel would increase dramatically. Stars would burn out before their light could travel far, and the universe would be a much smaller, more isolated place. Chemical reactions, which are governed by the speed of light, would be fundamentally altered, potentially preventing the formation of complex molecules necessary for life. Conversely, if Ca were significantly faster, the light-year distance would expand, but the energy released in nuclear reactions would be dramatically different. The binding energy of atomic nuclei, which is related to E equals mc squared, would be so large that stars might not be able to form stable, long-lived structures like our Sun. The universe would be a chaotic, short-lived place with no time for the slow, complex process of evolution to take hold. The light year is the distance that reminds us that the universe is fine-tuned for life. The value of the speed of light and the resulting light-year scale is one of the many cosmic constants that seem to be perfectly set to allow for the formation of stars, galaxies, and life as we know it. The light year is the distance that forces us to ask the most profound question of all. Why are the laws of physics the way they are? The anthropic principle suggests that the universe must be the way it is because if it were any different, we would not be here to observe it. The light year is the distance that defines the boundaries of our observable universe, and it is the distance that reminds us that our very existence is a cosmic miracle, a delicate balance of fundamental constants that allows us to look out into the night sky and ponder the impossible scale of the light year. The light year is the distance that breaks our brains, but in doing so, it opens the door to a deeper, more profound understanding of reality. It is the distance that reminds us that we are small, but our capacity for understanding is vast. It is the distance that connects us to the entire history of the universe, from the Big Bang to the present day. We have reached the end of our epic journey, a journey that has taken us from the finite speed of light to the infinite scale of the observable universe. We have seen how the light year is not just a number, but a profound philosophical concept, a measure of time, distance, and the limits of human perception. The light year is the distance that breaks our brains, but in doing so, it opens the door to a deeper, more profound understanding of reality. It is the distance that reminds us that we are small, but our capacity for understanding is vast. It is the distance that connects us to the entire history of the universe, from the Big Bang to the present day. The light year is the distance that inspires us to look up, to wonder, and to continue the quest to understand the cosmos. The night sky is not a static backdrop. It is a living, breathing history book, and every point of light is a word in the greatest story ever told. Thank you for joining us on this deep dive into the CosmoDepth. We hope this journey has ignited your curiosity and left you with a renewed appreciation for the incredible, complex, and beautiful universe we call home. Until next time, keep looking up.